Welcome everyone to today's webinar update on IEEE 1588 2019, PTP version 2.1 and PTP in wide area network applications, which is one webinar in a series of our remote session series, which started a few weeks ago, and we'll have another 3 webinars coming up every Tuesday, 1500 Central European Time. So again, welcome and thanks for joining in. My name is Andreas. I'm working for ALC Networks out of Munich. ALC Networks, the company who defines and maintains the RAVENNA IP media networking technology. We have a guest today. Our guest will be Daniel Bold from Meinberg. Daniel has more than 20 years experience with the development of synchronization products, and Meinberg is a German company based in Bad Pyrmont, established in 1979, and they are very famous and worldwide known for time and synchronization solutions across a large variety of industries. So it's not just broadcast, but also power, telecom, finance, and everything else. And they just recently acquired PTP technology supplier Oregano Systems from Austria. And Meinberg, just as ourselves, are very active in various standard organization bodies. So let's jump into the topic. Today's agenda. I will give a brief introduction on PTP version 2.1. This is the update on the IEEE 1588 standard published this year, but since it's finished last year, it bears the number 2019. And of course, I'll go through the discussion, is PTP version 2.1 a must-have or even a deal breaker for everything RAVENNA, AES67 and ST2110. Daniel will then take over and will describe what challenges you might encounter when transporting PTP across wide area networks. And of course, he will give some possible solutions and also has some real-life examples where PTP has been successfully transported over wide area networks. So that's what we'll cover today. Let's jump right into the topic. First of all, an update on IEEE 1588. So PTP, everyone knows this by now, is the precision time protocol, a standard which describes a protocol which allows very accurate transport of time across data networks. The features it features sub-microsecond time and frequency transfer, of course. It's very generic, so it can be applied to a large number of applications and industries, and it does this through the option of having PTP profiles. The first version was published in 2002, PTP version 1. The follow-up version was PTP version 2 in 2008, and the latest revision has been published this year, but has been finished in 2019, PTP version 2.1. Now, as we all know, PTP version 2.0, so the 2008 version, is the basis for synchronization in RAVENNA, AES67, as well as SMPTE2110. The way it works is we usually have a master clock, which by now most likely will be called leader instead of master due to some language issues which just recently came up. That master clock can or cannot or is not synchronized by GPS. And we have slave clocks, or followers would be the new term, which are synchronized using the PTP protocol. And from those synchronized local clocks, media clocks can be generated, basically any media clock, but as long as all devices generate the same media clock, those media clocks are absolutely precise in terms of phase and frequency. So they are identical, at least with respect to the requirements of the particular applications. That's the principle and how PTP is applied in RAVENNA, AES67 and 2110. Now, I also mentioned that various profiles exist, and this is not different for our media applications. We have the PTP default profile, of course, but AES67 as well as SMPTE2110 defined their own operating profiles for PTP. So the AES67 media profile is normative, but an optional feature for AES67. So AES67 devices need to run or need to have the ability to run on the PTP default profile as set forth by the standard. But for better operability, for better performance, AES67 has also defined the AES67 media profile. And likewise, SMPTE has defined the SMPTE 2059-2 SMPTE PTP profile for operation within SMPTE 2110 environments. Basically, both profiles have increased message rates or reduced message intervals for improved startup and accuracy, and have also added some other specialities like physical clock requirements in AES67 or management TLV metadata in 2059. The most important part, of course, is the increase or enhancement of the message rate. So if you look at the actual actual range of defined message rates, you can see minimum and maximum and default values for AES67. We have likewise the same thing for ST2110. And if you have a closer look, which we don't do in much detail yet today, you will see that there are differences in the default values. But if you look at the range of allowed values, there's a good overlap between the two profiles so that there is no need to run two different PTP profiles when you are operating AES67 and 2110 devices in the same network. And these commonalities and differences are summarized by a report which has been commonly written by the AES and SMPTE standard organizations. It's called the AES R16 2016, which nicely describes how these profiles differ and where the commonalities are so that you can find common operating parameters if you are mixing AES67 and 2110 devices in the same network to just run off one single PTP profile. So that document can be found on the AES.org website. So what about compatibility? PTP compatibility, we have 2002 and 2008, and by now everybody should know or actually knows that there is no backward compatibility. So 2008 was written in a way that it broke with the compatibility to the 2002 definition, so you can run devices either in 2002 or 2008 mode, and of course most of the devices today use PTP version to the 2008 mode. Now, so what about the 2019 revision? Will that break RAVENNA AES67 2110 operation? Well, to give the answer up front, well, to stay with Douglas, don't panic. We have seen that IEEE took the wise route of preserving full backward compatibility with version 2. So anything version 2.1 is compatible with version. The prerequisite was that full backward compatibility should be preserved with any new 2.x version. So backward compatibility actually means that any PTP 2.1 devices will work in 2.0 networks and won't compromise it. All additional features of PTP version 2.1, which will be, we'll have a look in a minute at, are optional features, so none of those are mandatory, and all PTP version 2.0 features will work as before. So that's just the assurance, don't panic, everything will run smoothly and we won't basically break anything. So what's new? PTP version 2.1 introduces enhancement and changes to make the standard clearer. Flexibility to the protocol has been added. Robustness features have been added. And options for increased accuracy have been added to 2.1. And it's interesting that some of these features have been taken from already existing PTP profiles, but they are now part of the core standard. It doesn't mean that profiles go away, and of course profiles can define anything beyond what is part of the core profile, but some of these features which were very identified to be very useful have been added to the core profile. So let's have a closer look at some of those features which have been added. Flexibility. Now Multicast and Unicast operation is a regular feature of PTP version 2.1. Basically, it's to decrease the load of the network by providing the ability to run sync messages in multicast mode and delay request and delay response in Unicast mode. That had been possible by configuration with 2.0 before, but now it's part of the core standard and one of the available operation modes. Modular transparent clocks can now be used. So that means that we can have a transparent clock built into an blade server or SFP architecture. The reason why this posed some difficulties before was that the stepness, the step 1 or step 2 operation had been a clock property and is now being changed to port property. So that means we can now have SFP-based transparent clocks. Also, special Ptp ports can now be defined. That might be useful when you're interfacing to different network technologies which have their own built-in timing mechanisms like EPON or Wi-Fi, so that you have a smooth transition between the Ethernet LAN-based Ptp modes and the particular or special timing mechanisms provided by other network architectures or methods, technologies. Robustness features have been added to Ptp version 2.1. The most important one is the profile isolations. It's now possible to run multiple profiles on the same network. Well, that would have been possible with 2.0 as well before, but only through means of different domain numbers, which was only possible with the configuration, which sometimes was a bit tedious and error prone. So now this is an integral part of the Ptp protocol. And for that reason, Ptp version 2.1 introduces a so-called profile ID, which can be assigned to standardization organizations. That's why it's called SDO ID. This has been introduced to preserve full backward compatibility with the existing Ptp messages. So let's have a quick look how this had been achieved. This is the common message header of Ptp version 2.0. Here's the one of Ptp version 2.1. So it's the same number of bytes in the header, same arrangement basically. But if you have a closer look, you can identify that in Ptp version 2.0 were some reserved fields, and those have been used now and been redefined for Ptp version 2.1. So now a Ptp version 2.0 implementation doesn't know anything of the new definition, but since they were reserved, it wasn't even looking at that. So through use of reserved fields, we have a full backward compatibility and can now run different profiles within the same domain on the same network. Interdomain interaction is a feature which adds to the robustness. The problem here was that sometimes relying on just one master clock would not be robust enough. If that master clock fails or was serving a wrong time, then you probably were without a precise time in your network. And for this reason, Ptp version 1 introduces interdomain interaction, where you can have several grandmasters on one network. They are serving their time on different domains into the network, and you can have a multi-domain clock which can adhere to different domains at the same time. So it's basically a device which can follow multiple master clocks, and it receives this through a single link into the network. So it's a common mean link delay towards the so-called edge switch on the network. And now the idea is that, of course, all the ordinary clocks within that multi-domain clock follow their respective master clocks, but through a voting algorithm, you can now build a very robust, resulting clock inside that device, so that even if one of those devices fails or serving the wrong time through the voting algorithm, you can still have a very, very precise and robust slave clock. So that is a part of the version 2.1 definitions. For security, the standard adds authentication TLVs, type length values for messages, adding source integrity checking. So a slave device can now see if the message being received is actually originating from the regular master clock, or if it has been an inserted fraudulent Ptp message. Standard performance metrics have been added to the standard as well. So we now have a standardized set of performance statistics available, which can be pulled or monitored within the slave device. And with that goes slave port monitoring. We now have a definition of TLVs which support active slave port monitoring. So data which can now be forwarded to a monitoring device for monitoring, diagnosing the whole network operation. Then in terms of accuracy, PTP version 2.1 provides some features that originate from the so-called White Rabbit project, which has been developed by CERN. And their target is basically to achieve sub-nanoseconds accuracy. We all know that with PTP version 2.0, it's good to achieve, let's say, 25 to 50 nanosecond accuracy in regular network operations. But for experimental and scientific applications, this was just not enough. So the White Rabbit project defined some extensions which allow to achieve sub-nanosecond accuracy. And I'm not going through any of these particular details here, but this involves manual port configuration. It can go hand in hand with physical layer 1 synchronization in synchronized networks. It has means for configuring timestamp and asymmetry correction, calibration, and all this is covered by the so-called high accuracy default PTP profiles. If you're interested in that one, there's good material available on the White Rabbit extensions to PTP version 1 on the internet. So let's summarize the new features just for a good overview. We have added more flexibility with version 2.1. We have improved robustness options, and we have increased accuracy. And besides that, we of course have some removed some ambiguities in the 1588 standards for better reading or clarification. Now, the base message is, or the main message is, we have full backward compatibility with version 2. So all PTP version 2 slaves will also sync with the PTP version 2.1 master. So is it a must-have now for RAVENNA AES67 2110, or just nice to have? Well, as I said, all standard profiles within those standards are referring back to the 2008 version. And none of these technologies or standards is broken actually by continuing to reference to PTP version 2.0 because they were operating just the way we needed them with the accuracy and precision we needed. And so that means that current and future system can actually rely on further using PTP version 2.0. However, if we look at version 2.1, which may be the most useful features, which well, some might want to have a closer look at. Certainly mixed multicast, unicast operations, particularly for large network environments, as we can find them in huge broadcast operations. The modular transparent clocks for setting up cloud environments, virtual environments, and the tight synchronization as they can now be moved to the SFP side of things. Profile isolations for running different PTP profiles might be useful here and there if we can't agree on a common profile. Inter-domain interactions, if you need more robust or higher reliability networks, might be a useful option. Security is always nice to have. And slave port monitoring is good to monitor reliable operation status. And if you're using wide area network applications, it might also be useful to use one of those special PTP port configurations options which are now part of version 2.1. So the question actually is, how can we evolve existing systems, devices towards PTP version 2.1? Well, there are two ways. One is the engineering way through system planning. Since we have the backward compatibility, we can at any time insert PTP version 2.1 devices safely into our network system without breaking the operations, and then the new features or improvements can be added or enabled as needed and supported by those devices. So that's the engineering way, by subsequently adding devices in those areas where we need additional features. Of course, there's also the standards way, which is then executed through the standardization organizations, so by AES and SMPTE, by carefully evaluating useful features, introducing those selected features into upcoming revisions of any of those standards, and of course, always trying to preserve full backward compatibility. And that should be possible, basically. So the summary is PTP introduces optional features which may be of beneficial for media systems. All enhancements are backward compatibility. Any of the existing technologies and standards are not broken by continuing to use and reference PTP version 2.0. And so the question, or the answer to the question, is it a must-have or a deal breaker, is simply PTP version 2.1 is neither a must-have nor a deal breaker, but it certainly can improve operation in particular areas where any of those added features may be beneficial. So that's it as a quick overview on what's new in PTP version 2.1. And that is the point where I hand it over to Daniel, who is presenting on how PTP can be successfully used in wide area applications and what challenges need to be overcome. Daniel?
Okay, thank you very much, Andreas. Okay, I would like to talk about PTP in wide area network applications and what are the challenges and what are the solutions actually. And afterwards, I will tell you something about a real world application. So we have basically three different challenges in wide area networks. The first one is a so-called unpredictable packet delay variation, or short PDV, that you will have when you send packets over usually non-PTP aware connection. So the packet delay variation reflects the packet jitter, which directly affects the slave's accuracy and stability. And this packet jitter leads to a so-called dynamic time error. That is a variation of offset around a value that is actually expected, ideally 0 actually. So here we have two PTP slave offset statistics. On the left side, you see a low PDV situation where you have typical values around plus minus 50 nanoseconds, and on the right hand side you have a high PDV situation where you have plus minus 500 or 600 nanoseconds in a scenario where you have more packet queuing in those switches. We come to this point a little later, but of course it can be even much higher than that in the range of microseconds or even milliseconds that you would have to deal with. So the reason for packet delay variation is basically that there are queuing delays in non-PTP aware network equipment, and the amount of the delay depends heavily on the switch performance and on the traffic load that is on these switches, because a PTP packet needs to wait actually before it's leaving the switch on a port. And if there is a large packet in front of the PTP packet that needs to get out a little earlier than the PTP packet, then it has to wait within the switch before it can come out. And therefore you have different latencies between master and slave, which leads to variation in offset and inaccuracies at the end. So the second challenge actually is the asymmetry between the receive and the transmit path. What does this actually mean? So you have, for example, a sync message that comes from the master to the slave, or now how it should be called, from the leader to the follower. And you have in the reverse direction a delay request message from the slave to the master. And it can be that they have different latencies, different times through the path that it takes. In this case, the master to slave delay might be 3 microseconds and the slave to master delay might be 8 microseconds. One example how this could be caused might be, for example, a link speed conversion between 1 gigabit and 100 megabit ports. Because if such a link speed conversion has to be done, then the switch needs to go into a so-called store and forward mode in one direction and can stay with a very fast cut-through mode in the other direction. And due to this store and forward versus cut-through technology, you get different latencies in both directions, which will result in a round-trip delay of 11 microseconds in total. And by design, the one-way delay is used and calculated to, which is taken into account in the offset calculation, which will result in 5.5 microseconds in total. So the real delay actually would be 3 microseconds. And this difference results in a constant time error of 2.5 microseconds in the end node. And you can actually do nothing about it if you don't have any ways to compare this against a reference or measure this asymmetry in advance. You cannot measure it from these two endpoints because there is still one unknown parameter within the math that you cannot automatically detect these asymmetries, and therefore you end up with those constant time errors. Okay, the third challenge within wide area networks and transporting PTP are network path rearrangements. What does this mean? So you have a path from grandmaster to slave, from the grandmaster on the left side to the slave on the right hand side, and you have two different paths that this signal can take. And usually path A would be chosen from switch 1 over switch 2 to switch 3 via switch 7 to the slave. But if an error occurs within the network, within this meshed network, then you cannot use this path anymore, and you have to choose another path that may consist of a different number of hops, different number of network equipment, or fiber optic lines that have different distances. And therefore, you can have different asymmetries also between these two paths. And if you now switch the path to path B, then those different path asymmetries will then, in the end, in the slave node, will lead to a time offset step, which you can see here in this real life measurement. So as this event happened, the time offset stepped from, let's say, 5.3 microseconds to 6.1 microseconds. So around 500, 600 nanoseconds of offset have been changed suddenly, and you have to deal with those events in the end node. Again, everything is run here now with a non-PTP aware network connection. So what can be the solutions? You have two parts of the solution. One is for infrastructure and one is for the PTP slave systems. So the solutions for the infrastructure, if ever possible, sometimes it's not possible in the first place and you have to deal with the infrastructure that's in place. But of course, it is always recommended that you use PTP-enabled switches or routers like boundary clocks or transparent clocks. If you can use a dedicated wavelength in a DWDM system, then you can separate the traffic from other traffic and use a dedicated path for the timing signals. Then you have, in this case, also like a dark fiber connection. Of course, this is often not possible or very expensive, but on the long term, it might be the better path for a future infrastructure. And on the other hand, you need a solution for PTP slave systems, or at least at the point where at the remote site, it can be a remote production site, it can be a remote studio, whatever, where the PTP signal enters this building or enters the system, and the PTP signal needs to be deployed locally in this environment. So you need there in these PTP slave system a high quality oscillator to allow a long-term measurement of PTP statistics and do some analysis of the incoming PTP signal, And while doing this analysis, you can maintain the stability of the clock with that high quality oscillator. Due to the fact that the situation can change over time, you need some advanced adaptive Ptp filter mechanisms, actually. Like you can see here in the graph on the right-hand side. This is a typical example of the difference between operating during the nighttime hours and during the day when everybody is in the office or everybody is using the network. Of course, this does not apply for 24/7 situations, but often you find these type of situations, and therefore you need some adaptive Ptp filter mechanisms to quickly adapt to those changes. Then you would need some asymmetry step detection mechanism because of the challenge that I described in the slide earlier. When you have path rearrangements, then you can have offset steps which might destroy your local Ptp stability. And if you want a clear reference to the real time, to the UTC time, you need link asymmetry calibration to start with the right value. If you are at the remote site, you can log to a reference like GPS, for example, before you end up with just using Ptp further on. So for this role, you would actually need a kind of gateway clock, or the telecom people call this an edge grandmaster, which will then provide a clean Ptp master signal to the local Ptp clients at the remote site while getting the Ptp from the network, from the core network on another port. So what's the situation actually? You can have something like this where you have a centralized, highly accurate core Ptp grandmaster here on the top right corner, transporting the Ptp signal through a non or just partial Ptp aware infrastructure, and you end up at the remote site, which then there locally might have a Ptp aware infrastructure, and there you can have a so-called PRTC or primary reference time clock with assisted partial timing support. This was a feature developed at the ITU for one of the telecom profiles, where you can have a GPS assistance to calibrate the path from the core grandmaster to the remote site. And as soon as GPS might go away or you lose GPS reception, then you can still use Ptp as a backup with a level of accuracy that is still acceptable for your local environment. So how do you deal with that? How as a vendor, for example, can you prepare for these situations? So you have a situation where you have, for example, from master to slave, approximately 100 microseconds of jitter. This is a simulated environment with a Ptp unaware path with up to 10 hops. And from slave to master, you have a little bit less jitter. And this is a typical situation, for example, also if you use the public internet, then you have much more traffic in download direction rather than in an upload direction. And therefore, you might have a little bit less of jitter. And this overall results in asymmetry of approximately 8 microseconds. So this situation can be simulated by an impairment generator, like, for example, the Paragon X from the company Calnex. So what do you do now when you receive all these Ptp packets? First of all, you analyze them. You get all the sync messages and you receive all the delay response messages at the slave, and then you just collect them for a couple of seconds and order them according to their one-way delays. So the master to slave delay and the slave to master delay. So you would select the so-called lucky packets, which are in fact the fastest packets with the lowest delays, and only use them and throw everything else away. And those lucky packet filters will reduce the packet delay variation dramatically, which will lead to a better slave stability. So how does this lucky packet filtering work? So on one side, you have a network with partial or no timing support where the PTP traffic comes from, and this will then arrive at the local PTP stack instances. And the PTP stack will then analyze all the timestamps from all the PTP messages and get this through a so-called lucky packet selector. And only the lucky packets will then be used to calculate the offset and the delay to the master, which then via a PLL will synchronize the local clock. So the lucky packet filters select some sync messages and some delay request messages to use and just discard all the rest. And the sync messages with the lowest master to slave time will be used. The delay request messages with the lowest slave to master time differences will be used, as these messages assume to have little or no queuing delay. So what's the result of this? So we did a 3-day test with the impairment generator with one of our units. And as I said before, it was simulating a jitter from master to slave with 100 microseconds, from slave to master to 60 microseconds. We used PTP packet rate for the sync and delay request for 64 packets per second to optimize the lucky packet filter. And we used GPS as an assistance at startup to automatically calibrate for the asymmetry. So the lucky packet filter, which is actually a pre-filter on the PTP card, reduced this incoming jitter to an offset variation of ±5 microseconds already. And this value, these offsets are now sent to the local clock filter. And this clock filter then reduced the jitter furthermore, again, down to ±300 nanoseconds, what you see here in this graph over 3 days. So with this technology, you can even get out sufficient accuracy, also even for 2059-2 scenarios to fully fulfill the demands that are specified in those broadcast-specific profiles. So now I would like to show you a real-life example that we did together with the broadcast station WDR in Cologne. And we have 2 scenarios. This is a network that is installed all across the state of North Rhine-Westphalia in Germany. And first of all, they started with a building-to-building connection within Cologne, just with a kilometer of distance, but with a full PTP-aware fiber optic infrastructure and with PTP-aware switches. And this PTP core ring, which is available all over the state, has used a default profile with 16 packets per second, because 16 packets per second is something that we recommend as a minimum to make use of this lucky packet filtering algorithm. And PTP-aware switches were used here in this scenario. So what you have here at the slave node is an offset variation of just about ±50 nanoseconds in total, which leads to a clock output locally for the local slaves to 20 nanoseconds. So this is a kind of GPS grade synchronization that you can achieve here via that high quality long range fiber connection. But what about a situation where you have a longer distance? And that's why we took another example from a studio, from a local studio in a different city, in this case in Dortmund, which is approximately 100 kilometers or even more, I'm not sure, from Cologne. And via the own maintained connection from Cologne to Dortmund via an MPLS network, where at the end a non-PTP aware router needs to be still needs to be used. This PTP signal has been sent. And locally, the PTP output is serving RAVENNA network for the radio production there in the studio. And over this connection, you have an offset variation of around plus minus 500 nanoseconds. And there you have also, we have also seen a step. This is brand new data. This is from the last week. And on November 19th, due to a network path rearrangement, there was a small offset jump of around 300 nanoseconds detected by the input, and the clock afterwards has detected that offset step and therefore decided not to follow this step and just subtract the step value from the incoming offsets, so that the clock was served with the same approximately the same offset variations as before. And even with getting in values of plus minus 500 nanoseconds, you could end up with an output accuracy of better than 100 nanoseconds due to the high quality oscillator and the adaptive filtering, which is way enough and sufficient for the RAVENNA network that was connected to it. And the benefit is that absolutely no GPS antenna installation on this remote site is actually required. So to summarize those aspects, you can have a GPS-free installation even on in remote production for PTP. But if you have a PTP unaware path from master to slave, then the accuracy is not guaranteed and is always subject to tests. So you always have to do a field test with the existing equipment that you have. You need a high quality equipment that receives those PTP packets and might filter the incoming traffic so that a clean signal for the local PTP slaves can be used there locally. It is possible, but there are some challenges that needs to be mitigated. So thank you very much.
If you like to have more answers to any of these topics, just turn to the RAVENNA webpage on the resources section, where we have plenty of material available regarding RAVENNA AES67 2110 and also PTP. But of course, regarding PTP, the Meinberg pages are always a good source of information. The Meinberg global page or the blog, which is maintained by Meinberg, which is very interesting and even more in detail information about PTP version 2.1, for example. That's it for today. I'd like to thank everyone who stayed with us until the end of this webinar. As always, if you have any further questions, please send out an email to ravenna@alcnetworks.de. If it's something particular for Daniel, I will happy to forward it. And otherwise, this is the end of today's webinar. And again, thank you, and hope to see everyone again next week, 1500. With the RAVENNA webinar sessions. Thank you very much.
Thanks, everybody.